Hello, my name is Marcio Wagner da Silva. I am process engineer at Petrobras. My presentation is regarding the solvent deasphalting as residue upgrading strategy and as a cheaper alternative to comply with IMO 2020. Well, our agenda is the relevance of residue upgrading to refiners' competitiveness, the residue upgrading routes, the carbon rejection against hydrogen addition, the IMO 2020, the challenges and opportunities, solvent deasphalting as residue upgrading strategy, the commercial technologies, the available commercial technologies for the solvent deasphalting process, the synergies of solvent deasphalting and hydrogen addition technologies, and to the finish, we prepare a review of the lubricant productions, a changing market, and a short conclusion. Well, the current scenario reveals the relevance of residue upgradation to refiners' competitiveness because we have stricter environmental regulations, a growing demand by petrochemicals, and the falling demand by transportation fuels. These scenarios create the necessity of higher bottom barrel conversion capacity for the refining hardwares. And for example, the growing of electric vehicles, according to EAA 2020, it's possible to see that the number of electric vehicles in circulation grew higher than 7 times in a 4 years interval. This is a strong contributor to the reduction of the transportation fuels consumption. Under this scenario, the reduction in transportation fuels demand, according to Wood Mackenzie in 2019, is expected growing demand by petrochemicals, and will let the the petrochemicals respond by the major part of the crude oil consumption in the middle term. Again, according now the data from Deloitte company, the growing market of petrochemical intermediates, the ethylene, propylene, benzene, and paraxylene, is this more petrochemicals implies in higher bottom barrel conversion capacity. And the residue upgrading routes available are the carbon rejection against the hydrogen addition. Carbon rejection involving normally thermal cracking process, and we have the catalytic cracking, the SEC as a catalytic process, solvent defaulting, the necessity of post-treating units, normally to attend the current environmental regulations, we need to post-treating units, normally the hydro-treating units. We have in the carbon rejection alternatives lower yields of high quality products according to the crude, lower operating and capital costs. For the other side, the hydrogen addition, we have deep hydrotreating units, hydrocracking technologies. They present higher yields of high quality derivatives, unfortunately high capital costs, high operating costs, and it's for the other side, these technologies are able to process high contaminant feeds, even for heavy crudes. Under this scenario, these characters, the hydrogen addition involve a higher capital cost, but with more benefits. We have some data from Shell Global Solutions, a comparative study, the relation about the capital spending with the residue conversion. It's possible to see that the solvent deasphalting is in an intermediate medium capex and the return over the investment. So the solvent deasphalting is in the middle of the higher the better benefit and the higher capital spending. Well, the solvent asphalting technologies is based of the residue stability depends on the equilibrium among the resin and asphaltenes. As it's normally the resin solidifies the asphaltenes keeping in a dispersed phase. It's used as solvent to to crack this equilibrium and separate the asphaltic oil and the asphaltic residue, which normally contains the major part of contaminants. We have evolution of the solvent asphalting technology is normally the the most employed process is the typical arrangement to solvent asphalting unit under supercritical conditions. The main advantage of the supercritical solvent asphalting technology is related to the energy consumption. It's lower than the conventional technologies. This process flow diagram is a schematic diagram for the ROSE technology developed by KBR company. Is one of the most spread technology for solvent asphalting that implies that apply the solvent in under supercritical conditions. Among the other available technologies, we have the Solvo process by Access Company, the SDA process developed in a joint venture from UOP and Foster Wheeler, the MAX process by UOP company. This diagram is a simplified process diagram for this SDA process. Well, the synergies between solvent deasphalting and other residue upgrading technologies. This diagram involves the use of the solvent deasphalting in combination of FCC and delayed coking unit. So, in this for our practice in a crude oil refinery applying this process arrangement, it's possible to achieve 40% of the middle distillates. Is a high yield in comparison with the capital spending. Well, for example, to use the hydrocracking unit. So the asphalted oil is applied to produce fuel oil in refineries processing low sulfur crudes. It's possible to produce bunker in compliance with IMO 2020, and the asphalted oil can be directed to the bunker or to feedstock to FCC unit in synergy with the delayed coking streams. Well, known technology developed by the Chevron Lumens company is the synergy of the solvent, the asphalting unit, with the deep hydrocracking. This technology is called LC Max, and where the solvent, the asphalting unit is applied in synergy with the hydrocracking. Normally, the asphalted oil is supplied to the hydrocracking to produce middle distillates and with higher quality. Well, the IMO 2020 presents a very strong challenge for some refineries, especially for those processing high sulfur crudes. This is a schematic diagram with how the bunker is produced. Normally, we apply vacuum residue, desalted oil, and dilutants, LCO, gas oils, to produce the bunker. After January of 2020, this task was harder because we have the reduction from 3.5% in mass of sulfur in the bunker to 0.5%. This is drastic reduction. So we need to control the the sulfur content in these streams. So the solvent deasphalting technology can be an attractive alternative to refiners processing low sulfur crudes with relatively low capital spending. Why? Because the solvent, normally the atmospheric residue, for example, in the Brazilian crude oils, we have the sulfur content varying from 0.4% to 0.6%. So it's possible to apply the asphalted oil to produce the new bunker in compliance with IMO 2020 with relative low capital spending, or applying just a small quantity of the hydrotreated diesel. Well, the lubricant production and the solvent asphalt technologies is a traditional route to produce base oils. This is a typical arrangement of the vacuum distillation process to produce lubricants. We have a first column to separate the atmospheric residue, and we have medium oil, light neutral oil, and the spindle. And the bottom of this column is fed to a new column that we have the heavy neutral oil, and finally the vacuum residue. The lubricant production through based on solvent deasphalting units is presented in this block diagram. We have, as aforementioned, the vacuum distillation section. We have the propan deasphalting, the vacuum residue is fed to the propan deasphalting. We have the heavier portion of called asphalt. The deasphalted oil is fed to the aromatic extraction section, and the hafenate oil is fed to a solvent dewaxing unit, and the waxed oil is normally sent to a finishing unit. It's normally involved in the hydroprocessing, light hydroprocessing unit to a mild hydroprocessing unit to produce the final base lubricant, while the waxes is treated in a wax oiling, and the oiling wax is again hydrotreated, and we can reach the wax to consumers. The main concern of the lubricant, the refiners relying exclusively of the solvent route to produce lubricants is the reduction of the group 1 and 2 to the base oil. We have the data from Statista in 2020, where expected in 2020 the reduction from 54% in 2015 to 39% in 2030 to the paraffin group 1, and the paraffin group 2 is expected to grow, but this is a trend of the technology development of the automotive industry to reduce the consumption of the base oils from group 2 and 1, putting under pressure the refiners relying only the solvent deasphalting technologies. So it's necessary to revamp these units, including the hydrocracking or mild hydrocracking technologies. Well, under our conclusions, we have refiners processing low sulfur crudes can find in the solvent asphalting technology an attractive route to meet the IMO 2020. Refiners relying on exclusively solvent asphalting technology tends to lose market share in the lubricants market due to the reduction in Group 1 and 2 base oils, as quoted earlier, and the synergy of solvent asphalt and another residue upgraded technologies like FCC and hydrocracking can ensure higher profitability and operational flexibility to refiners, especially related with the current the current chains faced by the players in the downstream unit. We strongly we strong believe that the downstream of the future is based on four pillars and the higher bottom barrel conversion, the petrochemicals integration, the clean hydrogen sources, and the renewables co-processing. So the residue upgrading technologies are fundamental to refiners achieve competitiveness in in the downstream of the future. Here we have some reference that we study to produce this presentation. It's a pleasure to take part of this amazing event. Thank you for the opportunity. Bye.